Now today we talk of an important concept. I won't give you the derivation. You look for it or try to derive it and you can send it. I can check it out. But it is a very important formula that is needed in any chemical systems, not only rocks, any chemical system. A very important theorem. I will tell you the background to this theorem. I will again start with a little bit from the basics. So we know that G or mu, whatever it is, either G or mu. Mu is the chemical potential. G is the free energy. Mu is equal to G by N, partial molar, or it's called the molar free energy. And that is a function of pressure, temperature, and excise. This is well known. Free energy, essential, is a function of temperature, composition, and mole fractions, all intensive parameters. They are not dependent on mass. And these parameters come in the Gibbs-Duhem equation as STT minus VdP plus sigma Ni d mu I is equal to 0. All this are intensive variables. All this are intensive variables. Now, for this, for a pure phase, G or mu, it doesn't matter, is a function of pressure and temperature. Right? G is a function of pressure and temperature for a pure phase. For an impure phase, G is a function of pressure, temperature, and composition. Written in terms of an equation, G is equal to G0 plus RT ln activity. This is where the compositional term comes in. We will do this later in great details. It's called plus RT ln x into gamma term, where A is equal to x into gamma, where x is the mole fraction and gamma is the activity coefficient. We will come to this very soon. But these are the basic equations that you should remember. For a pure phase, G is a function of pressure and temperature. That means for a pure phase, this doesn't work. For an impure phase, the whole thing is there. Remember, I told you, if activity is 1, which is true for a pure phase, then this term vanishes. So G is equal to G0. And G0 is essentially a function of pressure and temperature. Right? So now, with this, we start understanding a new way of looking at reactions. When we were talking of this one, and this is andalusite, this is sillimanite, and this is kyanite. And we can know, and you all know, that there are 3 reactions. 1, kyanite is equal to sillimanite. And then kyanite is equal to andalusite. And andalusite equal to sillimanite. These are 3 possible reactions. This is kyanite to sillimanite. This is kyanite to andalusite. And this one is andalusite to sillimanite. So this is 1, this is 2, and this is 3. Right? So we have 3 reactions. But you can see one thing, and remember, every reaction, here if we take as an Al2SiO5 as my chemical system, Al2SiO5 as my chemical system, then all these three phases, kyanite, andalusite and sillimanite, are pure phases. So if they are pure phases, the composition term does not come in at all. So each of these reactions are a function of pressure and temperature. Each of these reactions are a function of pressure and temperature, and they relate to a phase transition. Right? Yet, if you see, if I take 1 and 2 and eliminate kyanite, then I will get back this equation. Andalusite is equal to sillimanite. I will get it back. If I take kyanite and andalusite, this reaction, and I eliminate by algebraic addition andalusite, then I get back reaction, this reaction. So, out of the three reactions, we can see logically that two of them are independent reactions. The third one is a derivative reaction. That means, if you take any two reactions and algebraically add or subtract to eliminate a phase component, then you get the third reaction. So we have something called independent reactions. And there are some reactions which are called dependent reactions. So that's the key. So basically, if you have these two equations, these three reactions, out of this, only two reactions are independent. The other one is bogus because it's essentially a derivation. You add it and you will get the third one. What is then the formula? Now this is a simple system. One component system, Al2SiO5. A very simple system. And maybe it's very easy to see. But say you can have more complex systems. It's not that you can have, you will have much more complex systems. So in such complex mineralogical systems, is there a way to find out the number of independent reactions? The answer is yes. And the formula for that is very important. Number of independent reactions, possible independent reactions, is equal to number of phase component minus number of system component. That is the rule. Number of independent reactions is equal to number of phase components. Remember, phase components are those that describe the chemical variability of a phase. What are system components? Is the minimum number of components that describe the chemical variability of the system in which the mineral is. Now in this case, let's say you are here. Say you are here. This, as you know, is called the invariant point. If your chemical system is Al2SiO5, it is not an invariant system if the chemical system deviates from the ideal formula of Al2SiO5. It's not. It can be univariant, it can be bivariant. We have discussed this before. So now, let's say at the triple point, how many phase components are there? Kyanite is a phase, so it has to have a phase component because it's pure. it has one phase component. What is that? Al2SiO5 in kyanite. So that's the phase component. What is the phase component here? Sillimanite is a phase. So it has a composition and a pure phase. So it has one phase component. And similarly for andalusite. So there are three phase components. So if I write independent reactions, the number of phase components, it's called NP minus NC in short. Not very commonly used. Number of phase components minus number of system components. NS. Number of phase components minus number of system components. So how do we do it now? Number of phase components, how many? One for each of the pure phases. 3. Minus number of system component. Al2SiO5. Minus 1 equal to 2. There you are. The number of independent reactions in this is 2. Although you can write 3, 4, 5, it doesn't matter. Those are derivative reactions. The number of independent reactions is 2 only. Number is 2. Which one? It does not signify. Thermodynamics never signifies you, he, they. He says 3, 2, 1. You find out because you're supposed to be intelligent people. So this is how it works. And what are the variables here? Because it's a pure phase, the variables are pressure and temperature. Right? The number of variables are 2 here. Pressure and temperature. Here it's fixed, but how will you find it? 2 variables needed to be found out. So you have 2 reactions. 2 reactions means 2 equations. 2 equations, you can find out 2 variables. You can find out 2 variables. So then, there are 2 variables in this. Pressure and temperature. There is no other variable. No, kyanite, sillimanite, and andalusite are all pure phases. So composition is not a variable here. Right? So you have pressure and temperature. And you have 2 independent reactions. So you can 2 independent reactions means 2 equations. If you have 2 equations, you can find out 2 variables. That's how it is. But let's say you say Fe2SiO5. I go into the system, or let us, if it does not look nice to you, I can see. Cr2SiO5, chromium. So now what's happening? The system component now changes to 2. So I will write it. Here, the system component is 2 now. But what about the phase components? What about the phase components? How many phase components? Let's see. Kyanite, when it was Al2SiO5, it's pure. But now, if you add chromium, then your chromium replaces aluminium. So your composition is no more Al2SiO5. So the composition will vary between Al2SiO5 and Cr2SiO5 for kyanite. So how many intensive variables? 2 intensive variables. Isn't it? What is the intensive variable? Say for example for kyanite, how many variables will be there? Cr2SiO5, Al2SiO5. Which means to say XAl kyanite plus XCr kyanite is equal to 1. Now look at this. If this is the equation, then X aluminium chromium plus X aluminium is equal to 1, which means if you can determine one, then you can determine the other automatically. right? Because it's 1 minus that. Similarly, you will have for sillimanite and andalusite. So how many phase components are here? 2 for kyanite, right? N2SiO5, Cr2SiO5. 2 for sillimanite, N2SiO5, Cr2SiO5. 2 for andalusite, Al2SiO5, Cr2SiO5. So the phase components are 6. 6 phase components. Minus 2 is equal to 4. Is equal to 4. So in this system, which is Al2SiO5, Cr2SiO5, independent reactions are 6 phase components minus 2 system components is equal to 4. 4 reactions are available. 4 reactions are available. Just give me a second. Yeah, all is well. There are 4 reactions, independent reactions you can write. Achha, let us do like this. Let's write all the reactions possible. What are the reactions possible? We know there are 3 of them already here written. Since this system you have extended, all these reactions are there. Yes or no? Right? Also you can write, remember here all of them have the formula Al2SiO5. Or now I can write this in a slightly different way, if you don't mind. I will write it in a slightly different way or more clear way, because last time we had dealt with system component. Kyanite, Al2SiO5 is equal to sillimanite, Al2SiO5, what was the second one? Okay. Kyanite, Al2SiO5 is equal to andalusite, formula Al2SiO5, and then you have the third one is andalusite, Al2SiO5 is equal to sillimanite, Al2SiO5. Right? More specifically, I also can write 4. Kyanite, Al2. Now this time you see what I am doing. I have 6 reactions. He says 4 is enough. I don't want more. 4 is enough. Enough to find out what? It says you need 4 reactions. You need 4 reactions to do it. To find out what, and I can already see that I have 6. And there are more. There are 3 more. I will tell you what here. Can you anybody tell? Okay, we can't communicate. See here. 1. Okay, let me write this. There will be 3 more equations. 7. I'm writing it. Check it. Check here what has happened. Cr2SiO5 in kyanite plus Al2SiO5 in sillimanite is equal to Al2SiO5 in kyanite and Cr2SiO5 in sillimanite. You look at this. I will draw it with a blue pen so that you keep the connections. Look at this. It is essentially exchange of aluminium and chromium in silicon. And you see this? Exchange of chromium and aluminium in kyanite. You can have 1, 2, 3, 4, 5, 6 and 7, and you can imagine you will have 8 and 9. One for kyanite andalusite, one for andalusite sillimanite. You will have 9. And the Gibbs phase rule says, hey, I don't want so much, you just give me 4. I want 4 reactions. That means 4 equations. So if I have 4 equations, I will be able to find out 4 variables. 4 variables I will be able to find out. That is what it says. So you can write innumerable reactions, but all of them are not independent. They're dependent variables. You can see here. Look at 7. What is it? Look at 7. What is it? As written, it is related to, check here. It is related to 1 and 4. What have I done? This 7 is essentially a combination of 1 and 4. How? I have taken, you see here, it is 4 minus 1. 4 minus 1 is 7. You see, it's a derivative reaction. 4 minus 1 is equal to 7. So if you write 8 here involving kyanite and andalusite, I will tell you something. When you are viewing my video lectures, you just don't sit down like that. You can stop it, isn't it? You can give it a pause. You write it yourself down on the book. Don't just sit here. This is not a dancing movie. Yes, you take a pen, pause it and write it. And see whether I have gone wrong. So just don't look at the video lecture like this. It doesn't work. For metamorphic petrology, put pen to paper. First thing, put pen to paper. So you can do all what you can. So you can write your 8, your 9, and try logically. If I write 8 between kyanite and andalusite, it will be a similar reaction. Very similar reaction. But that will be a combination of 2 and 5 will give you 8. 2 and 5, 2 or 5 minus 2 will give you 8. 6 minus 3 will give you 9. So that is what happens. In a system, you will generate a lot of reactions, but all of the reactions are not independent reactions. Here, you can choose any 4 reactions and not derivative reactions. Say, for example, if you choose 1, 4 and 7. Sir, I have chosen 3 reactions. No. That and that are independent. This is not independent. That and that are independent. 1 and 4 are independent. 7 is not independent. Have you understood? It's very crucial. You have to be very precise with your thought process in metamorphic petrology. Very precise. If you go rummaging, you won't be able to work it out. You won't be able to work it out. And when you do my video lectures, remember, keep a book, keep a pen, and write down. Pause it, write down. Think. Go back, check again. Go forward, see what I have said, stop, do it. Do it, put pen to paper, not this. Doesn't help. Absolutely it will not help. So when I give you the problem, you will be lost. But put the pen on the paper and do it yourself. Take a system of your own. Take a system of your own. Small system, we will do it. Small system. And think about it. How can you face? What should I do? What is my objective? Now, in this, as I have written 7. You know there will be 8 and 9. So there are 9 equations. This formula takes you 4 of the equations. Any 4 equations are independent. Others are dependent. It's no use. It's a dog going round its tail. You have to take 4 independent reactions. One cannot be derived from the other. You see, 4 cannot be derived from 1. Or 1 cannot be derived from 4. But 7 can be derived from 1 and 4. So it's a derivative reaction. Have you understood? So, here you see, so you have 9 equations. And only 4 of them are independent reactions. In 4 reactions, so you will have 4 equations, so you can get 4 variables. Have you understood? This is the basic theory. 4 equations, you have 4 independent reactions. For each independent reaction, you will have a thermodynamic equation of state. So you will have an equation in pressure, temperature, composition. G is equal to Ptx, you will have a composition. And for that, you will be able to find out 4 variables. You cannot find out 5, or you cannot find out 6. You have to have 4 variables. Now my question is, what are the variables? What are the variables in the system? We know now, of course, pressure and temperature are variables. Pressure and temperature are variables. Then, okay, I will write it in a one below the other. That would be better. Pressure, temperature. XAl kyanite or X chromium kyanite. Or, I have written or, not and. Why? Because XAl kyanite plus X chromium kyanite is equal to 1. So one of them is independent. Then XAl andalusite or X chromium andalusite. XAl sillimanite or X chromium sillimanite. These are my variables. Pressure, temperature, 5 variables in all. I will be able to find out. I know that there are, my God, what's happening? I know that there are 5 variables in the system. This person says, you give me 4 variables, don't bother about 5, I will do it for you. But for the moment, you give me 4 variables. Now you can ask me, sir, how will I find the 5th variable? Wait a bit, I will tell you. But what it says is 4 independent reactions. That's what it says, and that's what's crucial for us. 4 independent reactions. So, now I will tell you, you add Fe2SiO5. Now you see, your system has not now 2, it's now 3. And your phase components will increase. And you do it, and tell me how many number of reactions you will need, and what are these reactions. Have you understood? So I give you this problem. Try to solve it. Take this extended system. The system components are 3 now. How many phase components are there? How many phase components? I will give you the hint. You do it, huh? You do it. You do it with a pen and paper. How many phase components? 3 here for kyanite. X chromium plus X aluminium plus X iron is equal to 1. Similarly for all. So how many variables? Out of which there are 3 plus 3 plus 3. 9 variables. Out of this 9 variable, there are 9 variables. Pressure, temperature, there are 9 variables. But Say for example in kyanite, X chromium plus X aluminium plus Fex Fe is equal to 1. One variable is lost. One variable is a dependent variable. Like I said, or is very important, not and. No, it's wrong. Or. Have you understood? You do it yourself and let me know how many independent reactions you have. If you have a problem, let me know. Let's then switch over to a little new one and see. Remember, say for example, I tell you, okay students, I have silica, I have a quartz in water. What is my chemical system? Let's say I have quartz. How many independent reactions? How many independent reactions? I have just quartz. My system is quartz. How many independent reactions? Immediately. Phase component, 1. What? SiO2. System component, 1. 1 minus 1, 0. No independent reactions. Okay. Okay, sir. I have a quartz in water. SiO2, H2O. How many, what is my number of equations? Write down. Number of phases, phase components. Pure H2O if it is, H2O. Pure quartz if it is, SiO2. Two phase components. What is the system component? SiO2, H2O. System component 2. Phase component minus system component 2 minus 2, 0. No independent reactions. You try it on anything and it will be true. Let's try it on another system, simple systems.